All right, so week 8, lesson 4, part 3. We're going to finish up various fitting techniques that we have. So in this week, I want to go ahead and look at the optimize command in scipy. So we're going to look at the creep analysis of a superalloy. This is the data for the lesson is going to come from your Callister textbook, and then you get to practice on some data that I pulled out of the web. So what we want to do is create a Larsen-Miller plot, and if you remember what that is, from 2044 we take data such as the applied stress, and at that applied stress we measure the time for a rupture of a sample at a specific temperature. So let's say we heat a sample up to 650 degrees C, and at 650 degrees C we apply, say, a temperature of 550 megapascals, and then we hold the sample at that 550. It continues to elongate through creep, and eventually the sample ruptures and fails. And in this particular case, it looks like it takes roughly 2 to 3 hours. Okay, and so that's the data that we have. For this data set, it was given in the Callister text. Since it's defined by lines, I'm going to just pretend there's a data point here at an intersection and at the end. And for the 815, we'll take a data point here, intersection 1, intersection 2, and then at the end. So then we can just fit lines or draw lines between the points. But I'm going to assume that's where the points are so I can reproduce this particular data set. So again, this is rupture lifetime in hours, stress in megapascals. Those are the units that we use in creep. All right, so one of the things that the textbook said is that if we were to take this data and replot it, we're going to keep stress over here, but now instead of rupture lifetime, we're going to take the log of that rupture lifetime. We're going to add to it some constant, which for this problem in your text was 20, and then we're going to multiply that value by the temperature in Kelvin. Okay, so we'll take each of the data points on these curves, multiply it by the temperature of the curve. And this factor of 10 to the third you can just ignore. This was because they divided 10 to the third out of their axes. So that's the plot that they got. So again, they took the data from the last curve, took the log of that rupture time, added 20 to it, multiplied by the temperature of the data, and this axis should be 20,000, 24,000, 28,000. They divided out each by 1,000. That's why they've got this factor here. Okay. So again, these are 20,000, 24,000, etc. But the data all collapses to one curve. At least that's what the textbook says. And so we'd like to go ahead and check and see if that's really the case. And then let's see if we can come up with a fitting routine that will allow us to collapse a different set of data where this value isn't necessarily 20. All right, that's our Larsen-Miller curve. And I'll also do a quick problem at the end, just showing you again how we used this to calculate lifetimes. So the first thing we're going to go ahead and do is to go ahead and use our select data and cal functions. So I'm going to go ahead and run this. And then we're going to go ahead and pull our data in. Okay, and so what we're going to have to do is we'd have to come here and rerun this several times. I'm just going to take 3 points. So that's my 650 data. So I'll go ahead and run that. That's my 650 data. Again, we'll copy that. I'll come down here and say data 650, and then I paste it in there. And so I've already done that, being a little bit more careful. Right. And so again, we just keep doing that. We'll come back up here and we'll run it again. That clears our pixel positions, and then we can grab another curve and so on. Don't forget that we also need to grab points for the corners like that. And again, I would run my pixel positions and I'd paste that into my pixel points. And here they are, again, when I'm a little more careful. Now this is a step we have to be particularly careful about, because this is a log plot, and our calibration function assumes linear axes. So that's not a problem. All we're going to do is to convert these two axes to a linear scale. And we do that by taking the log of the data and plotting that on a linear scale. And so what I would have then on a linear scale down here is I'd have the 0.5, 4, 3, 2, 1, 0, right? Just taking the log of each of these. Then on this scale, I'd have the log of 20, the log of 100, which is 2, the log of 1,000, which is 3. Okay. So when I put my points in, this point here is 5, and then the log of 20. Okay, this point here is -4, log of 20, etc. So here they are, the log of the plot points. Okay, so 0.5 and the log of 20. That's my point, right? -4, log of 20, then -4, and the log of 1,000 was 3. And don't forget, these are base 10 logs, so I need to make sure I'm doing that, where log would just be the natural log, and I don't want that. All right, so that's how I can take my points and putting the log plot points here just to remind myself that I have done this conversion. All right, so now we've got all our pixel points, we've got our calibration, we've taken the log of our plot points so that we're dealing with a linear calibration. So I go ahead and run this. And now I'm going to go ahead and take my pixel points, my log plot points, and then my pixel data that I have above, use my calibrate function to convert those all into plot coordinates. And then I'm going to simply go ahead and plot all of those. Okay. X values, Y values, blue, green, red, yellow, and I'm going to use circles for my markers. And I'm going to just go ahead and also label the text. These are the X and Y coordinates, and then my text. I'm going to put that on there just to make things kind of nice. So let's run it. Okay, and there's my plot. So notice, this is a linear scale because I've already taken the log of the data. So you would interpret this again then as 10 to the 4th, 10 to the 3rd, etc. So I've reproduced the data now, with now my axis being log of sigma, log of rupture time. And there's my 650, 730, 815, 925 data. Now I want to do is I want to take this data, each of these points, and so let's look down here. I've got the 650 degrees C data, which was called Cal 650C. Okay. I'm going to take the rupture time, so that would be my X position from that data. So this is my rupture time. I'm going to add 20 to it, and then I'm going to multiply it by the temperature, which is 650 plus 273. Okay. Again, I'm following this Larsen-Miller parameter here. So that's what I'll do for each of them. Take the rupture time, the log of the rupture time. Remember, we've already taken the log of it. And so here I just have to pull that off. I don't need to take the log of this. We've done it already. So that's convenient. But this is the log of the rupture time, I should have said here, plus 20 times the temperature. Log of the 815C, rupture time, plus 20, temperature. And so that's my new set of data. And we go ahead and plot that. And indeed, we get the data collapsing onto one curve. Okay, so these were my Y values that my X values that I pulled off and calculated here, the Larsen-Miller parameter. And then these were the Y values, which is the log of the stress from my previous plot. But you see, they do collapse onto one curve. All right, so what we can then do is we can go ahead and flip our axes, because what I want to do now is I want to have a polynomial fit to this data set so that under a given stress value, and rather than reading off here a Larsen-Miller parameter, I want to actually have a fit so that I can just plug the stress in and get the Larsen-Miller out. Okay. Well, that means I really want my data set plotted this way: Larsen-Miller here and stress over here. Right. So now I can fit this, and when I fit this, I'm going to have a function that is Larsen-Miller parameter is equal to, and then my polynomial fit, where my x values are the log of the stress. Then again, I don't need the graph. I can just use my nice polynomial fit. So I'm going to switch the axes like you saw here. I'm going to go ahead and define my fit. So this is just a polynomial fit. Okay. I'm reminding myself here that my x data is actually log of sigma. It's already the log, so I don't have to do anything special. I'm just going to put it in. But here is my polynomial fit. A1 times the log of the stress, A2 times the log of the stress squared, etc. I can add as many terms as I want here for my polynomial, or take away terms. So just this piece here would simply be a straight line. And then what I'm going to do is, to fit, I would like to have all of my data points together. So we're going to go ahead and stack them, horizontally stack them, which another way to do that is to append 730 data to the 650, then take that and then append the 815, and then take that result and then append the 925. So that's basically what we're doing here, just a little simpler. We're just stacking it, and it does the same job as the appending. All right, so I'm going to go ahead and append, or to stack that data together. I'm going to stack the Larsen-Miller parameter data together so that now I've got x and y data set for all of the data that we just plotted. Then I want to do is I want to combine these so that I have xy pairs, and that's what the zip function does, zip xy. It just now takes these two one-dimensional data sets and turns them into xy pairs of data. The zip actually creates what's called an object, and so I need to tell it to go ahead and convert that into a list. And then I'm going to convert the list into a NumPy array so that I can use my indexing that I like to use. All right, the next thing I want to do, since I just stuck this all together, the x values here are going to be all out of order, right? So I'm going to go from this one, this one, this one, and then my green's going to be over here. And so what I want to do is go ahead and sort these by their x values. And so this is the x values, the 0 position for my temporary array, which has these pairs. So I'm going to take the x values and then I'm going to sort them with argsort. And what this does is it returns the indices of each of the positions in here if it's sorted. Okay. And so then, since now this gives me all the indices of the sorted array, then I just simply put it back in and it'll pull out then each of the values in here according to this sort function. All right, so that's my sorted data. And then remember, this is now an XY pair, so I have all my XY data. So I'm going to go ahead and take the X data and call that my log stress, and then the Y data and call that my Larsen-Miller parameter. So that's where I've switched the two axes, Larsen-Miller and log sigma on the X. And then I'm going to go back and to what we did 2 lessons ago. In part 1, we used the curve fit routine. So here it is again. I'm going to curve fit using my function LM, which is a polynomial. Then I'm going to give it my X data and my Y data. And so that produces the fit, and it puts the fit into these. The output has 2 outputs, and this one's going to have my values in it. This one's related to errors for the fit and other parameters that I'm not going to use right now. So I'm going to use really just this one. All right, so we're going to go ahead and plot now my x data log sigma. Then we're going to grab the function here. Okay, we're going to put in log sigma, that's my x data, into my function. And then I want to put in A0, A1, A2, and A3. Okay, those values are given right here in this p.opt. And then I'm going to put a star on here. What the star does is, rather than having this go in, which currently is a list, it gets rid of the list brackets and puts them just in as values separated with commas. And that's what I need in this format. I don't want a bracket around these two as a list. So this is called a star variable. Again, just pulls the values out and gets rid of the extra brackets. So that's one way we can do that. So that substitutes it straight in, and we're going to basically plot this function. We're also going to go ahead and plot the data itself, log sigma, and then here's the y data. Okay, that's our data points. This is my fit. So we'll go ahead and run that, and this is what we get. So all the data together, Larsen-Miller, log stress, and this is my polynomial fit with my A0, A1, A2, A3 given here. All right, so let's look at a problem then, example. So let's say we want to know the rupture lifetime at 775 C with a 355 megapascal applied load. So what do? We want to calculate the Larsen-Miller parameter. So we'll go ahead and use our polynomial fit, which we called LM. Okay, we only need one value out, so we're going to go ahead and give it the log of the stress. So here it is, NP log base 10 of the stress, which is 355. And then we're going to give it each of these values. And so I now just copied and pasted them in by hand, just so you can see what we're doing without having that star variable confusing you. Otherwise, instead of writing all those in there like that, I could have just said comma, star, OPT, and then it would put these all in. But this is a little clearer, I think. So I put those in, right? There it is, A0, 1, 2, 3 in that order. And it's going to kick me back the solution to that polynomial, which is 20,247. That is my Larsen-Miller parameter, okay, which is equal to 20 plus the log of the rupture time times the temperature, 775 plus 273. So all I got to do now is solve for the rupture time. So there it is, rupture time, 0.21 hours. All right, so that's how long my component would last if made from that material with a 355 megapascal load at 775 C. It would fail by creep in less than a half hour. Okay, I'm going to stop there. In the next part, we'll go ahead and we'll look at where this C equals 20 came from and see if we can come up with a fitting routine that'll find that for us.